Kia ora, Year 12 and 13. This was a question in the 2015 differentiation paper about a cone of salt that was growing. So it's a related rates problem. It was an excellence question, and I think quite a few of you found it quite tricky. So this video is going to go very, very slowly. If you are already working easily at excellence level, you're probably going to find it too slow, so just watch the bits that you need. But for everyone else, I want you to try and pause it and work through it as we go, and try and anticipate what I'm going to do next. Okay, so the question goes like this. Salt harvested at the Grasmere Saltworks forms a cone as it falls from a conveyor belt. The slant of the cone forms an angle of 30 degrees with the horizontal, and the conveyor belt delivers the salt at a rate of 2 cubic metres of salt per minute. You're asked to find the rate at which the slant height is increasing when the radius of the cone is 10 metres. So we're going to start by saying let the slant height be x. And so the goal is to find dx by dt. Right, now I don't have one particular order that I do these problems in, but usually I do start by trying to define a variable, and then I start by writing down what I know that I've got. Well, we know that the salt is coming in at a rate of 2 metres cubed of salt per minute. So that's a rate to do with the volume, and this is a cone. So the formula for the volume of a cone is 1/3 times pi r squared h, and we've been told that dv by dt is equal to 2, right? So it's 2 cubic metres per minute. So we're starting to see the very start of a chain rule thing here. Now the easiest way to do this is to pull out this right angle triangle, write x in here, and start to play around with this. So here I've got h, and here I've got r. I'd like you to try and pause the video now and just see how far you can get with writing h as a function of something else in here, and what else you might want to do. And then I'll keep on going on the next slide. Okay, we're going to look at our volume formula. Right, we know dv by dt. Our goal is to get to dx by dt. So we're trying to set up some kind of chain rule relationship, and it's going to end with dv by dt. So we want to have something here that's linking how the volume relates to a change in here. Now, we're only in Year 12 and 13, so we can only think about differentiating functions of one variable. We've got two variables in here at the moment, and that's no good. We've got an r and we've got an h. We have to get rid of one of them. So we're going to use our right angle triangle. So here's 30 degrees, and this is what I've got here. Right, we know from trig what this looks like. So it's 1 here, √3 here. What can I say here? Well, this is my radius, this is x, my slant height, and this is my height. So I can easily link any two of those because I know my angle here. We can eliminate h. Right? We could also eliminate r, but I think that's going to be more work. So let's get rid of h, write h in terms of r. If this is my angle, this is my opposite, and this r here is my adjacent. So tan of 30 degrees is equal to h over r. So h is equal to r tan 30 degrees. Right, now we know, because it's a special triangle, we know what tan of 30 is. Right, it's 1 over √3. So, I'm running out of space here, but h is equal to r tan 30, which is r over √3. Now I can substitute that back in to this thing here. Now, one thing I should have said at the outset is the question is asking us about the rate at which slant height's increasing when r equals 10. A really common mistake is to start substituting that 10 in way too early. We do that right at the end of the question. The first thing we do is we get this general link between time, the rate of change of the slant height with respect to time. So now we can put h into my volume formula. I'm going to do that next. v is equal to 1/3 pi r squared h, which equals 1/3 times pi, where did I go? R squared times r over root 3. Told you this would be slow. So that's pi r cubed over 3 root 3. That means that now I can get dv by dr, which is the link between the volume and the radius. So that's going to be 3 pi r squared over 3 root 3, which is just pi r squared over root 3. Right, coming back to my chain rule, I'm still looking for dx by dt. My last bit is dv by dt. This bit is going to be how r and v work together, and this first bit is going to be the link between x and r. Right, so we've got dv by dr is equal to, where's it gone? dv by dr is pi r squared on root 3. So dr by dv will be root 3 divided by pi r squared. So that's that one. We've got that one, that's just 2. The last thing we've got to look at is the link between x and r. But that is pretty simple too with our right angle triangle. 30 degrees. Here's x and here's r. So this time it's going to be cosine 30 degrees is equal to r over x, adjacent over hypotenuse. X is equal to r over cosine of 30. But we know the cosine of 30 is root 3 on 2. Okay, so this side is 1, this side is 2, and this side is my root 3. So it's root 3 adjacent over hypotenuse. Right, now you see why at the start of the year when I told you about those special triangles that I was right. So x is equal to 2r on root 3, which means I can very easily get dx by dr. So dx by dr is just equal to 2 divided by root 3. So now we've got the enormous chain rule thing. Dx by dt is equal to dx by dr times dr by dv times dv by dt. Right, so 2 over root 3 times root 3 and pi r squared times 2. Right, let's see what disappears. Those two do. And we're left with 4 over pi r squared. So that's my dx by dt. The very last thing we have to do is we have to say, what is that rate when r equals 10? So in this case, we just have to substitute in a value that we were already given. Sometimes we'll need to go back to v equals blah 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 and work it out, but it wasn't that bad here. So on the next slide we'll put the numbers in our calculator at last. Dx by dt is equal to 4 over pi times 10 squared, which is 4 divided by, 314.15 da 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 da, as many values of pi as you remember, and that gives us our lovely answer, which is 0.01273, and it needs to be in metres per minute. Okay, it's in metres per minute because remember I'm looking at how the slant height is changing, right, not how the volume is changing. Okay, thank you very much for your patience. I know that was long, but that is a really nice example of a related rates problem where you just have to find the chain rule link, and it's usually going to have a Pythagoras, a simple year 11 trig, or a similar triangles thing going on. Okay, so there are more practice examples like this in Delta chapter 14.2. Please come and see me or send me an email if you've got questions about this one.